In this video, we're continuing section 10.1, which we're talking about curves and convex sets. So it kind of sounds like a little bit of an ominous start to the section, especially convex sets. Most people probably don't know what that is, but don't let this fool you. We're still talking about geometry and we're really working our way through plane figures, which is what the section's called. Okay, so let's start with curves. So we have a bunch of definitions again. A curve is a continuous set of points. Okay, let me say that better. A set of points, that can be drawn in a continuous motion. That's a better way of saying that. Okay, something like this. That's a curve. Okay, now we're going to get more refined in this. A simple curve so this is a curve that doesn't intersect itself. So the one above wouldn't qualify. Okay, so if I want to draw something that is in continuous motion like that, but doesn't intersect itself, I don't know, maybe something like this. Okay. Then we have the idea of a closed curve. So this is a curve that starts and stops at the same place. That's not how you spell starts. Starts and stops at the same place. Now notice it has nothing to do with intersection, okay? But it does have to do with having like a starting and stopping point that's, the same place. So here, let's just, I don't know, maybe the infinity symbol. Okay, that would be a closed curve. And here, I meant to underline these and I didn't because we are doing some definitions. And I like to underline the word we're defining. Okay, so putting those two ideas together, a simple curve and a closed curve. So a simple closed curve. Right, is a closed curve that doesn't intersect itself. And honestly, I don't know if I really needed to write this down since we defined the two words separately. All right, so an example of this would be having, well, here, let me do it like this. Let's kind of draw like almost like a little bit of a clover or something. I don't know. It's kind of weird looking. All right, but there you go. That would work. A simple closed curve doesn't intersect on itself, starts and stops at the same place. Okay, but I want to take this a step further. So this region inside of that, okay, if we kind of think of not just the curve on the outside, but also the region on the inside, that has a name too. So the union of a simple closed curve and its interior is a plane region, or is called a plane region. All right, so in that figure above, we're talking about both the curve and all of the inside of that curve. Okay, now let's kind of get into what they mean by convex set. So when they say set, they're talking about the set of points, or this, in this case, we're talking about regions. Okay, so I'm kind of giving these in a different way, these definitions in a different way. So a plane region is concave. That's what we call concave. if, oops, it contains 2 points where the line segment between the points, or between them, does not completely lie in the region. So actually, the example I have above does work for this, but let me draw a different example. Okay, I'll do kind of a simpler one, like a block U shape. So here, I have 2 points right here. And if I connect those 2 points together, that line segment goes outside of the region. So this would be something that is concave. So something that isn't concave, like, I don't know, something like this, okay? That's not concave. There's no way I can draw 2 points here that aren't going to be the line segment between them connected, right? It's got to stay inside this region, okay? They call this convex. So convex is basically something that isn't concave. So, oops. Alternatively, a region that isn't concave is called convex. So a convex set is a figure that's closed, and we're talking about both the curve and the inside region. So now when we kind of realize that that's what they say when they say convex set, that's not too exciting or scary, okay? And there are quite a few convex sets that you know of that have special names and special attributes. So let's get into them. The most, well, I think it's the most basic, is a circle. Okay, actually here. Yeah, that's fine. A circle. So a circle is a simple closed curve which has this special attribute where every point on the curve is the same distance from a fixed point. And we call that fixed point the center. So we draw our fixed point, right? And we're like, okay, so here's our fixed point. And then all the points on the curve are going to be the same distance away from it. It forms a circle. All right, pretend that's a circle. Now this is what we call the radius. If you're going all the way across, that's the diameter. If you draw a segment that doesn't go through the center but connects 2 points, we call that a chord. And if you have a line that only touches once, and typically then is outside, because it's the only way you can really only touch it once, they call that a tangent line. So there's the first basic convex set. The next basic convex set is a polygon. And I really hope you recognize that. This is a simple closed curve. Oops. Made up of line segments. Also, pretty darn basic, Okay, now we have quite a few polygons. Okay, so let's go through them. We have triangles. Or has 3 sides. And then next would be a quadrilateral. That's something with 4 sides. And here I'm going to kind of make it wonky. Doesn't have to be. We have very specific types of quadrilaterals and triangles. We'll come back and talk about those in a minute. 5-sided figure, that would be a pentagon. And the more like sides they get, the less likely I'm going to like draw the standard shape. Standard shape means like they're all equal sides. All right, I'm not going to do that. Okay, so sorry here. 3, 4, 5 sides. All right. Then we have a hexagon. Six sides. Oh, that's supposed to be an E. What can I do? Boop, 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 boop. 7-sided one is a heptagon with a P. Heptagon. All right. Now this one I'm going to get fun. I'm going to kind of draw. So 1, 2, 3, 4, 5, 6, 7. Pretending all of them are actually intersecting. 7. All right. Octagon. Used to be that when you heard the word octagon, most people thought of a stop sign. Now most people probably think of the UFC. It's all right. Here, like I said, I'm going to try to draw it wonky so I don't feel compelled to make it look perfect. I don't need it perfect. I just need it to have 8 sides. Okay, now we start getting into some of the less common ones. I think heptagon kind of qualifies as less common too, but same with a 9-sided figure. That's called a nonagon. Okay, nonagon. Let's see. Let's do 1, 2, 3, 4, 5, 6, 7, 8, 9. It's kind of like a house with a weird point, or farm, or a church. I don't know. Whatever floats your boat. 10 sides will be decagon. And now we're getting into, for those who are familiar with games that use multi-sided die, you might actually know some of the names of these, like a decagon. Okay, so 10 sides. Here we go. Let's see. 1, 2, 3, 4, 5, 6. Sorry. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's do this. 7, 8, 9, 10. I don't know what the hell you want to call that. Oh, a rocket ship. All right. And then they skip 11 sides. And I honestly don't know what it's called. You could Google it if you want. But they get to 12 sides for some reason. And that is a dodecagon. That's so fun to say. Dodecagon, 12 sides. Here we go. Let's draw one. Okay, 12 sides. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So exciting. I love it. And there you go. Polygons. Okay. Now, I'm going to talk about specifics with triangles and quadrilaterals in a second. I want to just go through a little bit of vocabulary really quick for polygons, okay? So here, let me just kind of draw a polygon for us to refer to. And here, we'll make it a pentagon. Okay, there we go. All right. So each of these corners, okay, and I'm just putting dots on them for right now, just to kind of give them a distinguishing feature. These are called a vertex. A single one is a vertex. Multiple are vertices, okay? When two sides are next to each other, they call those adjacent sides. And then two vertices next to each other would be adjacent vertices, okay? And then if you draw a line from non-adjacent vertices, that is what they call a diagonal. So a diagonal connects non-adjacent vertices. And there we go. Okay, so here, let me give, I know we've just been doing a lot of vocabulary. Let me give like an example. So a huge amount of these examples are like, you know, classifying shapes and figures and whatnot, okay? But this would be an example where maybe we could use some vocabulary to kind of do something. So let's draw as many diagonals as possible on a hexagon. Okay. So I'm going to go ahead and draw a hexagon to start. All right, kind of went for the basic. I'm just going to, again, give myself kind of points at the corners just so I can work from that. All right, so diagonal. So I'd like to start typically at 1. And if you want to pause the video, by the way, and do this yourself, do it. Go for it. I'd love you to try it, okay? Figure out how many diagonals we can draw, all right? But I like to start at 1 vertice and kind of go to every other non-adjacent vertice, all right? So that would be, like, I'm going to start on the top left one here. So from here to here, that's 1, 2, 3. Okay, and now I'm going to go to the one on the right now. I'm going to do the same thing. 1, 2, 3. Okay. And now I'm going to go to, I'm going to just keep kind of following the clockwise motion. So for that vertice, let's see, we can connect this. 1, 2. Okay. And then the only other one, if I go to the next one, it looks like I can connect these two. And that's it. I believe we're all connected. So just to kind of count those up, let's see, there was 3 here. 1, 2, 3, 4, 5, 6, 7, 8, 9. There we go. 9 diagonals, which I'm going to write down as my answer. Cool. Okay, now let's go ahead and talk some specifics about triangles, and then we'll jump into quadrilaterals after that. Okay, so for triangles, here, different types. So we have some triangles that are kind of named for the angles themselves, okay? So like we have a right triangle, which has a right angle. We have an acute triangle. An acute triangle would mean that all of the angles are less than 90 degrees. So 1 90-degree angle. And this is all angles are less than or just say acute. I don't know why I would bother saying it. All angles are acute. We know what an acute angle is. We defined that earlier. All right. And then there is an obtuse triangle. With an obtuse triangle, like with a right triangle, we have one obtuse angle. All right. And then when all of the angles are equal, we call that an equilateral triangle. And with an equilateral triangle, not only are all the angles equal, so are all the sides. So all the angles and the sides are equal. So now we're going to kind of get into triangles that also have kind of things going on with the sides themselves. Okay. So an equilateral triangle. Then there's what's called an isosceles triangle. With an isosceles triangle, two of the sides are equal and one is not. Now I'm using those little like lines through to indicate which sides are the same length. So, right, notice I have two of them that have the single line through them. That's indicating those two are equal. And the reason I put two here is to indicate that one's different. It's different than the other two, so it has a different length. Okay. So with isosceles, two equal sides and angles. Again. Then we have a scalene triangle. Here, I'm going to kind of do it exaggerated. A scalene triangle has no equal sides or angles. So you'll notice that in all of them, they talk about the angles. Okay, the angles themselves do get discussed, but there are some properties, especially when you start talking about lengths of the sides, that also directly correspond to angles that are the same measure. All right, now quadrilaterals. So with quadrilaterals, we have several types as well. So we have a trapezoid. Here, I'm going to intentionally try to make it so that one diagonal side is kind of longer than the other. Okay. So what's true about a trapezoid, which makes something a trapezoid, is that you have only one set of parallel sides, or one set of sides are parallel. So on this picture, these two would be the parallel sides. They use kind of like an almost an arrow to represent parallel in geometric figures. Okay. Then it's possible that the two diagonal sides are the same length on the trapezoid. And if that's the case, that would be an isosceles trapezoid. And I'm not going to write that down, like the descriptor, because I feel like we have both the definition of a trapezoid listed and isosceles. And of course, I indicated two of the sides are equal by the lines. And then, of course, these two are parallel. I could draw those two arrows if I wanted to kind of emphasize that. Cool. Okay, then we have what's called a parallelogram. So similar in that there's parallel sides. Here, I'm going to exaggerate it a bit. Sorry, I want to make sure because some of them have different names. And I want to make sure we get it. Okay, so on this one, we have opposite sides that are parallel. So opposite sides are parallel on both sides, right? Not just one set, and also equal, right? They're in equal length. So these two are equal to each other, and these two are equal in length to each other. Okay. If all, oh, I just realized I did that in red instead of green. I have to be consistent. I'm sorry. I have to erase it. I'm just that OCD. Okay. Sorry. Opposite sides are parallel. Okay. Sorry. If all the sides are parallel and equal, all four sides, okay, that is kind of like a diamond. And in that case, we call this a rhombus. Doing green. So it's a parallelogram with equal sides. So all the sides happen to be the same length. Okay. Then we can get into parallelograms that not only have the sides where they're parallel, but angles have some interesting things. So like this, a rectangle. So a rectangle is a parallelogram, except it has these right angles. So a parallelogram with right angles. And just like the parallelogram we drew above, opposite sides are equal and parallel. And we all have right angles. So all the angles are equal as well. Unlike the rhombus. With the rhombus, the opposite angles are equal, but they're not all the same, right? We have two that are obtuse and two that are acute. Right triangle, I'm sorry, right rectangle, we have all of them are 90 degrees. Okay, and then a special example of a rectangle would be a square, where not only are all the angles equal, but all the sides are equal as well. So all angles and sides are equal. All right. And you'll notice that something like a square could be thought of as a special example of a rectangle, or a special example of a parallelogram, or a special example, well, not really of a rhombus, because the idea with parallelograms and rhombuses typically is that they don't just have the, it's those right angles, the fact that they are equal. But yeah, you kind of get the idea. They kind of get more specialized as we go with the angles and the sides. And there you go. That is the convex sets.